be talking about some of our work on bringing AI to the physical world. So the state of robotics right now is in a pretty challenging spot, which is that if you want to truly solve a robotics application and actually deploy robots for real in the real world, you essentially need to build an entire company around that application. You need basically a different company for robots in logistics, wet lab automation, a different company for cooking in kitchens, for surgical robots, and so forth. And creating these companies, you need to make new hardware, you need to develop custom software for that hardware, design unique movement primitives for the application, handle edge cases for that application, and so on. And you need to do all of that from scratch, building on kind of very little foundation. This makes it really, really challenging to actually see real robots in the physical world successfully solving our problems. And this is the problem that the company that I co-founded, Physical Intelligence, is aiming to solve. We're aiming to try to build a generalist model that can enable any robot to do any task. And our main thesis is that we think that such a generalist model will actually work better and be easier to use than purpose-built models. And this is, in some ways, somewhat counterintuitive, but it's actually the same thing that we've seen happen in the language modeling industry, where you no longer use a special purpose model for answering email or for tutoring. You use kind of the same general purpose-based model that has kind of a broad capabilities and broad knowledge across many applications. And essentially, kind of analogous to how many companies are trying to bring intelligence to the digital world, we're aiming to bring intelligence to the physical world. Now, how do we actually do this? This is quite hard, quite challenging. And if we were to take a lesson from the success of language models and the success of tools like ChatGPT, we might kind of learn that scale is really important. We need really large-scale data sets, large-scale compute. That's really been at the backbone of making these approaches successful. And so if you were to take this lesson, one possible conclusion that you might take is that scale is the most important ingredient for being successful and for solving this problem. And let's say that the conclusion is true. If this is true, then we might look to things like data from industrial automation, because we can get massive scale from data from industrial automation. And yet, this sort of data is going to lack diverse behaviors, and we're not going to learn how to cook meals or bag groceries from this kind of data. Maybe instead we could look to data from YouTube. But in terms of videos of humans doing tasks, it's very rich. There's a lot of scale. But there's a significant embodiment gap between humans and robots. And even humans, for example, don't learn how to play tennis successfully by watching videos of Roger Federer play tennis. And then lastly, we could also look to simulation. We can also get massive scale from simulation, but yet there's also a huge reality gap between simulation and the real world, where the physics and the visuals are different, and thus it's actually pretty challenging to use this data. And so kind of the point here is that I think scale is really important for solving a problem, especially in the age of, kind of in AI and in the age of modern models, but it's subordinate to actually solving the problem. And the approach that I'm betting on and that my company is betting on is using data, large amounts of real-world data, to build these kinds of models. And to start off, we can start by collecting data through teleoperation. So here's a video of Kyler teleoperating the robot. You can see Kyler somewhat in the background. He's holding kind of what are called these leader arm devices, and you can use them to essentially puppeteer the robot, where you can measure the kind of the angles on the arms that Kyler is holding, and then project them onto the robot arms that are in the foreground. And you can do pretty challenging tasks like light a match through this sort of teleoperation. And what I'd like to talk about in the main part of this talk is some recent results that we've had, and basically where the state of physical AI, physical robots, is at using fairly large-scale real robot data. And by large scale, I mean by today's robot standards. This is still smaller generally than the data sets that we see to train language models and to train kind of state-of-the-art foundation models, but are still much larger scale than, say, the data sets we were training on even just a few years ago. And specifically, I'll talk a little bit about kind of where the state of physical AI is for dexterous long horizon tasks, for generalization to new places, and to the ability to follow open-ended prompts. And at the end, I'll talk a little bit about what I think are some of the open challenges and kind of why this is still a continuing open research problem. Great, so in this first part, I want to talk a little bit about how we trained a robot to do this. This is a video that we took actually about almost 1 year ago exactly. And so it's a little bit old by AI standards, but I want to talk about it because at least to me, this is actually still the most impressive thing I've ever seen a robot do. And specifically what it's doing here is it unloaded 5 items of clothes from the laundry, from the dryer, and then it's proceeding to fold all 5 of those items and stack them neatly. This is far from perfect. You can see right here, the robot is kind of missing some grasps, making some mistakes. It is eventually able to recover and figure out how to fold this shirt. And this video is sped up, but it actually only takes around 10 minutes to unload and fold these 5 items of clothing, which, at least in my mind, is still like blows my mind in some ways. Yeah, it was a lot of fun working on this particular project. And this is actually something that I worked on personally quite a bit, along with Michael and Suraj on this laundry application, and of course with support from the entire physical intelligence team. Cool, so how do you even get started on something like this? So at the beginning of the company, we started with kind of like what you can sort of think of as unit tests for robotics. And so we started with, can we start with a single size, single brand shirt starting flat on the table, and can we also dynamically flatten one shirt? Fairly simple control tasks. And our recipe is that we're going to collect data through teleoperation and then train a neural network or a policy, something that's going to map from observations like images and joint angles to target commanded joint positions. And we're going to train this with imitation learning. So essentially, the neural network is going to be trained to mimic the demonstrations that were recorded by a person. We're going to start with a pretty small model with around 100 million parameters. It's going to be mapping from images to target joint positions at 50 hertz. And so in May of 2024, we were able to get a pretty good policy for these simple tasks. So here you can see I'm kind of like flattening the shirt on the table and then asking the robot to fold it. And the robot can kind of do a decent job at this kind of basic version of the task. We also wanted to test more dynamic motions, which really stresses your ability to kind of match the training conditions and the testing conditions, especially in terms of inference speed. And we see that the robot is able to do some dynamic motions, which is pretty promising. And so this is in kind of May of last year. And then from there, we wanted to make it gradually harder towards the demo video that I showed at the beginning. And so what we did is we then kind of used the same recipe, and we started with the crumpled shirt on the table. And it turned out this actually made it not just gradually harder, but a lot harder. And so here are kind of videos of that recipe, training with imitation learning, and the robot really struggles to make progress and kind of figure out how to handle the shirts in different crumpled ways. And we measured the success rate of this. I ran experiments. After many experiments, the robot was really struggling with this sort of recipe. We started at some point to see some signs of life. This was kind of maybe a month and a half later in late June. For the first time, we saw the robot be able to kind of flatten the shirt and then eventually fold it. This is 8x speed, so kind of struggling, but at least some initial signs of life. Well, we can wait for it to fold it here. So some signs of life. So we decided to kind of move on to the kind of complete or more complete version of the task where you have a laundry basket. And there's multiple items in the laundry basket, and your goal is to kind of fold them and stack them. Now, this turned out to still be really, really hard. And once we moved on to this setting, we kind of still saw very little success in training this. And while we were working on this, we considered a lot of different things. We thought, okay, maybe the robot needs memory, because our models didn't have any memory. Maybe we just need to train for longer. We need more compute. Maybe we need to consider a different way of representing the actions. Maybe our encoders are miscalibrated. We actually knew that they were at least somewhat miscalibrated, but we didn't know if that was affecting it. Maybe we need to condition the model in certain ways. Maybe we need hierarchy to kind of break down the task into smaller chunks. Maybe our images are too low resolution. Maybe we need interventions. Tried a lot of different things. And generally, we're kind of struggling and had around 2 to 3 months of failure at this task. It's turned out to be really, really challenging. And the thing that really seemed to actually start making a dent is when we moved to this paradigm of, instead of training on all the data, first pre-training on all the data, and then kind of post-training or fine-tuning the model on a curated, high-quality set of human teleoperated demonstrations. And this was this is the video of the outcome once we started following that recipe. And kind of the night that we got this video, I was really excited because this is the first time that the robot was able to fold 5 items in a row successfully, which was really, really cool. This is in September of 2024, so multiple months after kind of the first unit tests. And it took about 20 minutes to do it. So the kind of what it's told us is that this sort of recipe really seemed to be really important for actually starting to kind of get this to work. Now again, it makes many mistakes, and in this case, it actually took 7 attempts at the blue shirt, and the quality of the folding varied quite a bit. We also saw other failures. Here's another failure that we saw a few times where it would stack the items and then try to adjust the stack a little bit, and then maybe adjust it a little bit too much and dropped it off the table. Cool, and then we kind of, once we had the skeleton of this recipe, we felt like we could optimize it even more. We then fine-tuned on even higher quality demonstrations, and then we're able to bring it down from 20 minutes down to 12 minutes, so a pretty significant jump in performance. We also still saw some varying quality in the folds. And then at this point, so we were working on kind of training these 100 million parameter models. There was a separate team that was working on pre-trained vision language models. And this is where we could actually start to combine what we were working on with what the pre-training folks were working on. And so specifically what they had here is, on the left, a pre-trained vision language model. This is a large language model backbone. It was an open source vision language model. The Polygemma model developed actually by Google and open sourced by Google with 3 billion parameters. So we're going to a model that's around 10 times larger. We pass as input between 1 image and 3 images, depending on the particular robot. We also pass as input a language instruction. And then we have this kind of separate action expert that's using what's called diffusion in order to predict, use the joint angles to predict kind of the next second of target joint angles or actions. And so what we did is we then took this model, we trained it on all of the robot data that we had, and then fine-tuned it using the same kind of pre-training and post-training recipe that we had before. And so before we were only pre-training on all the laundry data. Instead, we pre-trained on all of the robot data that we had. And then we just took the same exact post-training data set and applied it to this new pre-trained model. And we saw that the robot was actually able to perform quite a bit better just by swapping out the pre-trained model. And so before we were doing like 5 items in around 12 minutes. Now we were able to do 5 items in 9 minutes or 4 items in 5 minutes. Kind of there's some variability depending on the items. And we also saw a lot more consistent quality in terms of the folds. So one thing that was kind of cool here was we were able to decouple kind of the development of the pre-trained model and the development of the kind of post-training data curation. And we often see this sort of decoupling between pre-training and post-training in language model development as well. A few highlights of what the robot had learned. So these are shorts that the robot has never seen before. And it's able to learn fairly nuanced strategies where, like, in a minute, it's going to learn that it has to kind of reach underneath the shorts in order to kind of be able to flatten the shorts on the table. And then after this, it will kind of fold the shorts and continue. It's also able to figure out how to find corners. So at this point, it needs to kind of find the corner, the bottom corner. It actually kind of gets it to a more crumpled state in order to find the corner and then eventually flatten the shirt. And then we can also handle unseen clothes. So in this video, we have kind of a V-neck shirt. It hadn't seen any V-necks before. We weren't really focusing too much on generalization here, but it was nice to see that it was able to handle some clothing items that it hadn't seen before. Later in this video, there's also a shirt that has kind of buttons on it that's also able to handle. And then the last thing I'll mention on the laundry side is it's also able to handle interruptions. So this is kind of a policy that's constantly reacting to images that it's seeing. And so Michael here is taking the shirt out of the bin, and the robot decides to put it back so that it can fold the current item. And here's another kind of interruption. So Michael, again, is going to mess with the robot. And so the robot will then continue to fold. I think that was the last time. There we go. Cool. So that was kind of our work and basically kind of the way that we developed this sort of recipe for laundry folding. And we can also do the science and actually measure if this is better than the other recipes. So the pre-training plus post-training recipe where we kind of adapt it on a high-quality set, that was kind of the recipe that we developed. We also compared to training only on the curated data and not using any pre-trained model on other robot data, as well as just not doing any post-training and just training on all of the data. And what we find is that if we measure task progress, so we're going to be measuring, like, you'll get some score if you just get the object out of the bin, another score if you flatten, fold, and stack. And so there's a large difference between like getting it out of the bin and folding, for example. And we see that with the pre-training and post-training recipe, we see like a far greater performance compared to excluding the pre-training step or excluding the post-training step. And this is like really, really massive difference, and this is like the previous two recipes are essentially what we were trying to do before we ended up at the recipe that was using both pre-training and post-training. And then the last thing that I'll mention is like we're using machine learning here, we're learning from data, and there's nothing specific in this recipe for laundry. And so we can actually apply this same recipe to all sorts of other tasks. We use laundry as a test bed because it's really challenging, but we can also then apply this recipe to cleaning up a table, to being able to scoop espresso beans into a coffee grinder, being able to fold a cardboard box, as well as being able to autonomously light a match. And all of these are things that are like quite dexterous and quite challenging to do prior to these kinds of this model and this sort of recipe. The other thing that we can do is, this is a robot developed by a company, a different company, Astrobot, and I've actually never seen this robot in person myself. No one at Physical Intelligence has seen this robot. They sent us some data. We fine-tuned the model on the data that they sent us, sent them back the fine-tuned model, and with a little bit of back and forth, we were able to get a fine-tuned model that worked quite well on their robot, despite the fact that this is a different robot platform, a different country, and so forth, in comparison to all the experiments that we had done previously. Cool. So the takeaways for this part is that we were able to kind of independently develop this kind of post-training recipe and this pre-trained model, and that generally kind of just throwing all of the data in wasn't able to effectively work for these sorts of complex tasks. And that we were able to kind of progress gradually from simple folding tasks to the full laundry task in order to kind of achieve the kind of complete, really challenging task. Now, there's one limitation, or one kind of really glaring limitation that we saw when we completed this work, which is that the robot was trained in like one apartment or in our office, but it isn't able to then work in a new apartment or a new office building. And so this is what we really tried to tackle next. So we were looking at robots can do really dexterous tasks, but they can't succeed in new places. Can we actually get these AI models to generalize to completely new places? And we considered the task of tidying bedrooms and kitchens. And we wanted to be able to drop the robot into a new home that it had never been in before and ask it to clean the bedroom or clean the kitchen. To start off, we need data. And Again, kind of unlike like language, for example, we don't have Wikipedia for how to tie your shoelaces. We don't have kind of internet web data for robotic control. And so we collected some data ourselves. We collected data across homes in San Francisco, as well as across diverse mock bedrooms and mock kitchens, covering more than 100 different unique rooms. And then we slotted this data into the existing data that we had on our robots as well. So the full data mixture for pre-training contained this diverse mobile manipulation data, wheeled robots with 2 arms, alongside diverse static robots that are just kind of mounted to a table, data from the lab with a variety of robots, web data, and high-level instructional data. And one of the things that I'll point out here is we had this kind of full data mixture, and the diverse data in diverse homes, this actually only accounted for 2.4% of the overall kind of pre-training data mix. And so this kind of points towards a world in which we can kind of spin up a new task and a new robot without having to redo all of the data collection process. And so then if we kind of imagine a new robotics application that we want to be able to spin up, we don't have to invest kind of a ton of effort into kind of then like from scratch being able to spin that up, because we can just collect a little bit more data on top of what we have and add it to the repertoire of capabilities of our robot. There's a couple challenges in doing this beyond the data side. So in the early development, we found that kind of Pi0-based models can ignore language instructions. And so here I'm asking it to pick up the cutting board. The robot first ignored me and picked up the blue plate. Now it's ignoring me again and picking up the pink plate. I said, fine, put the plate in the sink. I'm again going to ask it to pick up the cutting board. It tries to drive away a little bit. I tell it to drive right, and then pick up the cutting board, and it finally listens to me the last time. And so one of the things for this particular challenge that we thought about is that we know that the base kind of polygemma, the open source language model, knows how to follow language well. And so maybe we just have to preserve that in order to allow the robot to follow instructions. And so the core idea here is that if you look a little bit into the details of the Pi0 architecture, this head on the model, it's randomly initialized parameters, and this is actually not very good at pre-training, or not good at preserving the knowledge in the base model. And so what we could do instead is we could actually predict tokenized actions so that we don't actually have to change anything about the base vision language model. So just like how we predict language tokens, we can predict kind of these action tokens, fine-tune the model, stop the gradient from the diffusion head from kind of destroying the knowledge in the backbone, in the vision language model backbone. And if we do this, we saw that the model trained 4 to 5 times faster, and it also followed language far, far better, 80% of the time instead of 20% of the time. Cool. So combining this sort of training recipe that I talked about briefly with the data that I mentioned, we were able to develop a new model, which we called the Pi05 model. And we tested it in homes that the robot had never been in. So this is a home, a kitchen that the robot has never been in before. We kind of brought the robot there. We didn't collect any data in this particular home. I asked it to close the cabinet. I asked it to kind of put the dishes into the sink. And at the end, I'll also ask it to wipe the spill on the counter. And the robot is able to kind of be able to handle, do all of these tasks in like a home that it has never been in before. So without any sort of data in that environment. We also, not just kitchens, but we also then kind of packed it up, brought it to a new home that it had never been in before. And Laura here is going to ask it to clean the bedroom. In this case, she's actually giving it less instruction than what I did in the previous video. And so, yeah, I guess also in addition to the environment being held out, all of the clothing, the linens, the layout of the room is all held out. This is really, really hard because the robot has to be able to adapt its perception, its control, its high-level planning, all to the variability of this new environment. We tested it in some other homes as well. Quantitatively, we can also kind of experimentally look at what actually mattered for getting this sort of generalization. And we see that the recipe with all of the data in yellow does significantly better than if we exclude data from static robots. And so we actually see significant transfer from just table-mounted robots to these more mobile robots. And then we also see that as we increase the number of environments in the data set, the performance on a new home increases significantly well and actually closes the gap to a model that was trained on data from the target environment. So the generalization gap goes to near 0. Cool. There's also some failure modes. As with kind of the previous model, like none of this is like succeeds 100% of the time. We saw that the success rate was around 80%. We can look at some of the failure modes. In this case, we told it to put the items in the drawer. The robot opens the drawer, roughly puts it in, says that's good enough, and drives away. We tell it to put the clothes in the laundry basket. In this case, it picks it up, accidentally drives over the shirt, and isn't able to figure out that it needs to drive backwards in order to pick it up. Here we told it to put the dishes in the sink. It actually, in this case, it was able to put the first 3 items into the sink, but then struggles with the cutting board. Generally, like very thin objects are pretty challenging to grasp, especially with these particular grippers. And then my favorite example, we told it to put the spatula in the drawer. The robot decides that this looks a lot like a drawer. And so maybe it'll try putting it in here. Also, the challenges with speed, with really long horizon tasks, and with partial observability where the robot can't necessarily see everything from its own cameras. Cool. So the takeaway here is that with much more diverse data, we can actually allow robots to follow, complete multiple tasks in completely new environments. This was definitely, I think if you're not in robotics, it's hard to fully grasp how challenging this is. This is really, really hard to do. You have to deal with all sorts of variability in the environment. And then the other thing that the last kind of core part that I'll mention is that here, the instruction set is somewhat limited. It can follow commands like clean the kitchen, clean the bedroom, put the items in the drawer, and so forth. But ultimately, just like language models, we might want to be able to prompt a robot in any sort of way, just like we type in a prompt into ChatGPT and say, oh, can you help me with this? Or give a fairly detailed kind of interjection and prompt to this. So how might we do this? How might we allow robots to handle any sort of instruction? We're going to consider hierarchical models in this case. And we're actually going to have a high-level model take as input the prompt, and then essentially translate that into a low-level command that will then be passed to the kinds of models that I was talking about before. And so this high-level vision language model, you can sort of think of this as kind of like a model like Gemini or ChatGPT. It's going to interpret the user input and then generate language commands, simplified language commands for the low-level policy or the low-level model to follow. So maybe it'll say, maybe the prompt is something like, oh, can you make me a vegetarian sandwich? I don't like pickles. Then it's going to say, OK, the next thing the robot should do is pick up 1 slice of bread. And then the low-level model is going to then actually execute that on the robot. So it's going to be responsible for taking as input, pick up 1 slice of bread, and then figure out how it should actually control the joints of the robots in order to do that. Now, this doesn't solve the problem on its own. This is kind of a step towards it. But this kind of high-level model doesn't exist already. And unfortunately, models like GPT and Gemini aren't able to just kind of slot into that top model right now. And we need a way to be able to handle open-ended language. One of the things that we do here is that if we want to be able to handle all sorts of prompts, it's really expensive to try to collect lots of different human-robot interactions, because it means that we need to then have humans in the loop of the robot data collection process. And this is going to be pretty challenging. And so instead, what we'd like to be able to do is we might actually be able to use language models to kind of simulate these kinds of human-robot interactions. And in particular, we can take the robot data and then relabel it with hypothetical prompts that could have led to the particular situation that the robot was in. And this can then kind of sidestep the need for kind of human-robot data, instead just take the robot data and augment it with the kinds of situations that might run into. So maybe the next thing the robot is about to do is to pick up a Kit Kat. Then the language model can then kind of generate a particular prompt or a particular situation that might have led to the robot picking up the Kit Kat. For example, maybe the prompt in this case could have been, hi, robot, can you get me something chocolatey? and so forth. And then we can use this to then kind of train a high-level vision language model that can handle all sorts of different prompts that the language model came up with. Cool, so with this approach, we're able to then give the robot a lot more detailed prompts. So we can say, hey, robot, can you make me a ham and cheese sandwich? And then the model is going to then kind of translate that for the model, like pick up one slice of whole wheat bread, put it on the chopping board, pick up one slice of cheddar cheese, put that on the bread, pick up one slice of ham, and so forth. And then it could also follow other prompts, like, hi, robot, can you make me a vegan sandwich? I don't like pickles, though. And they could then kind of break that down and comprehend what that means for what the robot should do next in the video on the right. So these are kind of pretty long horizon tasks. This can also handle interjections. On the left, the user actually asked, oh, can you add more pickles? And the robot was able to do that in the middle as well. This is kind of a step towards kind of trying to enable the promptability kind of a ChatGPT, except in the physical world. We'll let the robot finish the vegan sandwich. Cool. We can also then kind of test the model with different prompts. So on the left, we didn't use any sort of prompt. And by default, the robot in this case will put the dishes in the bin and put the trash in the trash can. Then we can also tell it on the right, clean up only the trash but not the dishes. And this will then kind of affect how the robot actually behaves in that environment. And it will then leave all of the dishes on the table rather than putting them away. So it gives us essentially a lot more control over what the robot is able to do. And I think this is going to be really critical in the future, where we actually will have humans and robots kind of working together to complete tasks rather than robots operating entirely autonomously. Then lastly, we can also do situated corrections. So in this case, the robot picks up a Kit Kat. The person says, get me something sweet that's not in the basket. And then the robot decides that it'll get some Skittles for the user. Cool. The last thing that you might ask is, can we just take an existing off-the-shelf language model and just replace that with the high-level model? And what we found, these experiments kind of were before GPT-5 came out, but we tested GPT-4o and just slotted it into the high-level policy, and we found that it really kind of lagged in performance compared to actually using real robot data. And since then, we've also tested models like GPT-5, Gemini 2.5, and so forth, and also find that they aren't very good at the sort of kind of situated physical reasoning that's required to understand how to break down a task into shorter instructions. Cool. So to summarize this part of the talk, we saw how robots can complete dexterous long horizon tasks, how they can succeed in places they've never been in before, and how they can reply to and complete open-ended prompts and interjections. The other thing that I'll mention is that we've actually open sourced the Pi0 and Pi05 models and trying to kind of, in an attempt to try to foster an ecosystem around these kinds of physical AI models. And we've actually seen a lot of people use these models and apply them to robots that we didn't even think would necessarily, these models would be very useful for, like surgical robots, quadcopters, and so forth. And so, yeah, it's been really encouraging to see kind of the ecosystem and see people kind of leverage these open source models in lots of different ways. The last thing I want to emphasize is that robotics, it's really, really exciting to see all the progress and see what robots are capable of. But it's also still, many aspects of it are still an open research problem. So I think that we'll be pretty close to deploying these models in real use cases and towards being really useful. But there's also, in many other scenarios, kind of really miles to go before like fully solving this sort of problem. And to highlight this, I wanted to highlight just a few examples of challenges and some things that we're doing active research on in my lab at Stanford. And so one thing that you might be surprised about is that state-of-the-art robot models, basically all of them have no memory. And they can't remember anything that happened in the past. This means that if you have a task that requires some sort of memory, like you want to dust these shelves and then put the items back where they were, then if you apply a model without memory, it's going to forget that it already dusted the shelves and then try to dust them again repeatedly. And then might try to put objects back again and then decide, oh, okay, maybe I need to dust the shelves again. We've been doing a little bit of research about kind of integrating frame retrieval and integrating memory into these models so that they can actually complete tasks with memory, but this is like really bleeding edge research. It's actually a paper that we released like a week ago on arXiv. Also research, another open research problem is how to actually enable robots to do tasks at the same speed as humans. Humans are really incredible in terms of the actual manipulation skills that we have. And a lot of the videos that I showed previously are sped up so that you're not bored kind of watching the robot fold laundry for 10 minutes. And so there's a lot of kind of open questions around how best to do this. One way to do this might be through more intuitive interfaces for collecting data on the robot. And we've done a little bit of work on kind of developing such a teleoperation interface where you're directly holding the robot and show that you can kind of train a robot to fold shorts in 6 seconds. So kind of promising signs of life there. We may also be able to use kind of trial and error learning from the robot's own mistakes in order to get faster behavior. And so in this case, we trained the robot to pour almonds in around 4 seconds. So both of these videos are 1x speed, not sped up at all. And in both of these cases, we saw about a 2 to 3x improvement in speed. And then lastly, a lot of the models that I showed before are often peaking at around 80% success rate, or sometimes even lower than that. And to truly deploy these models in real-world situations, they need to have a higher reliability than 80%. And so things like reinforcement learning are really exciting tools for doing that. And we've been developing some efficient reinforcement learning algorithms in my lab. There's also some exciting work that was shared, that was released yesterday by NVIDIA that fine-tuned the open source Pi0 model with reinforcement learning to get like a really high reliability on this GPU insertion task. Cool. So to close out, kind of the 3 main takeaways of what I've talked about are, first, this kind of thesis that general purpose robots are actually going to be more successful than specialist or purpose-built models, following the kind of the same trend as language models. Second, large-scale real data is going to be really important for actually addressing this physical intelligence problem, but not sufficient, and we still need more research. And generally, before robots will be ready to tackle the real world, we need to kind of figure out some of the open challenges that I mentioned. Cool. I should also mention that physical intelligence is hiring, and so if you're excited about some of the working with robots and so forth, feel free to look at the open roles. And then also would like to acknowledge the really, really amazing people that put a lot of work into what I shared, and happy to take some questions.